Hello and welcome to Vodcast 11.5. This vodcast is focused on temperature controls, and while developing our conceptual understanding of temperature controls, we are going to consider a variety of climate case studies. By definition, a temperature control is any factor that causes temperature to vary from place to place and from time to time. Now, there are a variety of factors that can affect the temperature in a given region. For instance, latitude, elevation, proximity to a large body of water, the prevailing winds, and I could continue to go on. But what I'd really like to stress at this point, that's an important concept that you may or may not know about, is that water has an extremely high heat capacity. And what that means is water can absorb enormous quantities of solar energy and stay at relatively the same temperature. Land is not capable of doing that. Land will heat up pretty quickly and it'll cool down pretty quickly. But water can maintain a very consistent temperature, even despite whatever the land masses around it are doing. Maybe you've had this experience, and I know I have, but if you've ever tried to go swimming on a hot day in April or May, you may have been jolted by what felt like ice cold water when you jumped into the pool or the lake or whatever you were jumping into. Despite the fact that the temperature might be in the 80s on that given day, it will take a lot longer time for that water to warm up than it will for the surrounding land to warm up and for the atmosphere to warm up. That's the big picture concept that we have to keep in mind throughout this video podcast. Oceans can serve as very, very effective regulators of climate. There are a few key considerations I'd like you to keep in mind, and they're in red font. First, land will heat more rapidly than water. Second, land will get hotter than water. In other words, on hot days, land will reach a higher absolute temperature than water. By the same token, land will cool off faster than water. So for instance, at night, the land can cool quite rapidly once that solar energy is no longer being provided. And finally, land can reach much cooler temperatures than water. You may have seen this firsthand if you've ever been to Chicago during the winter. And while there's snow on the ground and the ground is frozen, Lake Michigan is still liquid water. I'd like to start off by considering a somewhat busy image, but we're only going to focus on a couple curves that you see on this particular graph. I'd like to start off with the city you're probably most familiar with, and that's St. Louis, Missouri. I want you to notice a few things about that red bell curve that you see on the screen. First off, the bell curve tends to peak in the summer months of July and August. And that makes sense because on the vertical axis in this particular graph, we're talking about temperature, and St. Louis will experience its highest temperatures in the summer months. But in its winter months, St. Louis will cool down pretty significantly. The average temperature in St. Louis in December is below 40 degrees Fahrenheit, and then if you go back to the other side of this graph and look at the red line, in January the temperatures are actually closer to 30 degrees Fahrenheit. I'd like you to note that there's a pretty big temperature range between the summer months and the winter months for St. Louis. This bell curve kind of looks like a really towering mountain. Now at this point I want to look at a map to explain the reason why this bell curve is so towering. St. Louis is located right in the middle of the United States of America, so it's essentially landlocked. And what I mean when I say that St. Louis is landlocked is that there is no ocean even remotely close to St. Louis. Typically speaking, whenever we're looking at a landlocked area in the mid-latitudes or the upper latitudes, you will tend to see pretty towering bell curve peaks, just like this one we see in red for St. Louis. In fact, if you look at the blue curve for Winnipeg, you'll notice that its shape and its height are very similar to the curve we see for St. Louis. It's just shifted down a little bit from St. Louis because Winnipeg is at a higher latitude than St. Louis. And generally speaking, the higher the latitude, the cooler the average temperatures will be. Now, I'd like to compare the red line that you see for St. Louis to the green line you see for Cape Town, South Africa. The first thing you probably notice is that our bell curve looks like it's upside down. And the reason that this bell curve is upside down is because Cape Town, South Africa is located in the southern hemisphere. What that essentially means is that Cape Town's summer months will occur during our winter months, and Cape Town's winter months will occur during our summer months, because we're located in the northern hemisphere and they're located in the southern hemisphere. So the lowest temperatures you tend to see in Cape Town occur right around June, July, August. And for St. Louis, it's pretty close to the opposite. Now, one other thing I want to point out that's very important is that you may notice that this bell curve isn't as extreme as the St. Louis bell curve. And what I mean by that is that the valley you see in green isn't a very deep valley, whereas the mountain peak that we talked about for the St. Louis bell curve is pretty high. Now, when I'm talking about valleys and mountains, what I'm essentially referring to is the temperature ranges that you see in one of these cities between winter months and summer months. The highest temperatures you'll see in St. Louis are going to be somewhere between 84 and 85 degrees on average, as shown here at the top of this red curve. The lowest temperatures that you'll see in St. Louis are going to be right around 30 degrees, and those occur in January. So the temperature range for St. Louis will be somewhere around 55 degrees when comparing the coldest that it'll get in the winter to the warmest that it'll get in the summer. However, Cape Town's temperature range is only going to be about 15 degrees when comparing the coolest it'll get in the winter to the warmest that it'll get in the summer. Why is that the case? Well, let's take a look at a map that shows Cape Town's location. Cape Town is on the windward side of the Atlantic Ocean. And what I mean by that is that the prevailing winds will be coming off of the Atlantic Ocean and onto land, right where Cape Town is on the coast. We call these prevailing winds the westerlies in the mid-latitude regions, and Cape Town is in the mid-latitude regions. Now, as mentioned on the previous slide, very large bodies of water can serve as climate stabilizers, and the Atlantic Ocean serves as just that for Cape Town. And although Cape Town and St. Louis don't have huge differences in their latitudes, we do see huge differences in their temperature ranges. And that's simply explained by the fact that one of them is located near a body of water where the prevailing winds are coming off of that body of water, and then one of the locations is landlocked in the middle of a continent. I'm not going to talk very extensively about what you see on this slide, but if you'd like to pause the video and kind of take it all in, I hope it makes sense based on my descriptions from the previous slide. The keys to understanding why Vancouver's bell curve looks much different than Winnipeg's bell curve is the fact that Vancouver is near the Pacific Ocean on the windward coast. And here in the continental United States and up into Canada, the westerlies are the prevailing winds. So the prevailing winds tend to come off the Pacific Ocean, and that helps stabilize Vancouver's climate. The temperature range in degrees Fahrenheit for Vancouver only looks to be about 20-22 degrees or so. Now Winnipeg, located right in the middle of our continent, is landlocked. During the summer months, Winnipeg will get warmer than Vancouver, because remember, land will heat up more than water does. But during the winter months, Winnipeg's temperatures will plummet, because by the same token, land can get much cooler than water as well. The key concept to remember is that water has a high specific heat. And what that means is water is capable of maintaining a fairly consistent temperature. However, on the flip side of that coin, land tends to have a very low heat capacity, meaning land can heat up rapidly when it's warm, and land can cool down rapidly when it's cold. But long story short, your landlocked areas will see much greater temperature ranges. Now in this particular plot, the difference that we see between Concepcion and La Paz is based on altitude or elevation. La Paz is located at a fairly high altitude in the mountains, and Concepcion is pretty far east of that mountain belt. What this plot basically shows us is that altitude can also have a substantial impact on climate. That probably makes sense if you've ever seen the Rocky Mountains and you've seen the snow caps towards the top of them. The higher you go up into the mountains, the colder it'll get. Other important controls include geographic position, cloud cover, and albedo. Okay, I'd like to conclude this video podcast by asking you to complete a self-quiz. You see two plots shown for the annual weather data from two locations, specifically Decatur, Illinois and San Francisco, California. Which city corresponds to the red plot and which city corresponds to the blue plot, and how do you know? Take a moment to pause the video and answer this question, and then when you hit play, I'll provide you the answer and give a brief justification. Okay, welcome back. To answer this question, you should have said Decatur, Illinois will be the red plot and San Francisco, California will be the blue plot. The reason that the red plot would correspond to Decatur, Illinois is the fact that Decatur, Illinois is landlocked. In other words, it's located kind of towards the middle of the United States, and there's no ocean nearby. In the summer months in Decatur, the land can heat up very rapidly, and you'll tend to see far higher summer temperatures in Decatur than you would in San Francisco. But in the winter months, land can also cool rapidly, and you see that the temperatures tend to plunge as Decatur enters its winter months. Now, San Francisco, California is on the windward side of the Pacific Ocean, and what that basically means is that the westerlies, which are our prevailing winds, are coming off of the Pacific Ocean and influencing San Francisco's climate. Due to that fact, San Francisco won't have a very big temperature range between its winter months and its summer months. Okay, that concludes this video podcast. I hope it's helped you kind of understand some of the controls of climate. And if you need additional examples of these plots, let me know, because I can definitely come up with them. In our next video podcast, we will consider worldwide temperature distributions for the summer months and the winter months.